that's me. And we are going to talk today about ahead-of-time compilation again. Probably some of you listened to my talk last year. Is there, yeah, that's an agenda. The topics would be quite simple, and they will be, we'll talk about current solution, and the main focus will be what happens with performance naively and really, and what approach do we use to deal with it. This slide says that you may not believe me and you must not believe me, and not to make any commercial decisions based on my talk. All right. So, in JDK 9, there is now an AOT compiler. From the end of last year, it was build 150. And it's based on Graal. The slot before, there was a talk about Graal a bit. It was about truffle, and there are talks about Graal. And the version of Graal for AOT in JDK 9 is more or less fixed, and it's probably not the latest one, but that's the one that was tested. So you can just grab it and use it. Look into JEP. It is pretty self-descriptive. There are all instructions on how to use AOT, how to compile the code. Or you can watch some of my presentations. Okay, so it's a simple addition. Besides of the main flow, where your code is compiled by Java-C and then loaded in VM and JIT compiled, interpreted, etc. You can also do native compilation ahead of time. Right, that's an ahead-of-time compiler. Great. So there was a set of problems, targeted problems for AOT. And there's probably a larger set of problems that were not targeted. Of course, well, we'll look at some of them. So, with AOT, I'll walk through this briefly. There are modes, they're different. Particularly, I'll mention tiered and non-tiered modes of AOT, where you go and reach peak performance using a last tier compiler, dynamic compiler, or non-tiered mode, where you stay in the same code as in the very beginning of execution of your program. And what happens next? Next, it will be Java 10, Java 11, etc. And the announced goal is to have more Java on Java. And then you may ask, where do we find Java on Java? Yeah, of course, there are some parts of Java code in JDK already. Of course, it's class library, and there are other parts. And you may consider more, like rewriting parts of runtime and replacing compilers with compilers written also in Java. Okay, so there is now a single name, code name, and a single project announced one. It's called Metropolis. You can easily find talks that mention it, or probably soon you will be able just to look at some repos, etc. All right. So I'll show some results, some numeric ones. They are mostly based on the build that's not too old. Current one is like 169. So that should be fine. The qualitative picture is not changing much from using different machine or something. Okay. So naive approach would be to take some benchmarks that benchmark the and to compare AUT-generated code and code that's generated by dynamic JIT compilers, right? Okay, we have VM benchmarks, not so relevant at this time, but they are still actively used. They can be any code names, but well, there are some real names of big JVM benchmarks. Anyway, we'll just take AUT, particularly in this case, it will be tiered one. We'll take regular tiered compiled execution as the opposite, and we'll compare them. So what do you see here? I'll show you another part. What do you see here and there? There's no difference, right? That's a naive approach. We took tiered AUT, which transits then to JIT code. So in an ideal world, there's nothing left of AUT in the hot, in the warmed up execution, right? That's good. It actually shows that it acts as expected. So not bad. Okay. Then let's try to do some better thing. We'll go on with non-tiered AUT. Let's compare true AUT code with JIT code. They're using the same benchmarks. So what do you see here? I see that in some cases there is no difference. Wow. Those are different compilers, and there's no difference. So it's good. In some cases, the difference is, well, it's impressive. It may be tens of %, which is also good, actually, because it's much, much better than interpreter. And like, if you'll try to design and build and productize some compiler, it's hard. It's a hard task. It's a hard problem. Okay. So we know that Graal is used for AUT, Graal compiler. So we may just take Graal. It's now possible to enable it, use it instead of C2 in experimental mode, and to look if that difference in cases, then there is a difference, if it's because of Graal is used or not. And what we see is sometimes it's because of Graal, and sometimes it's not. Well, the result is probably obvious, but it has to be proven, right? So you see that lines. All right. So what do we do next? What do we have? What's about AUT? There are a number of libraries that are automatically loaded. I mean, if there are libraries, native libraries that were AUT generated and they are placed in started place and they have standard names, they will be automatically loaded and linked and used by VM. So we can just start looking at them. How do you start looking at library? It's a file, right? A file has a size of file. And those libraries are really huge. And we can compare them to something, for example, to module files. Well, they are bigger. All right, but you may notice that that size depends on configuration of the library. For example, if we use different garbage collector, or of course, if we just strip debug information and the size will differ. What's there? Yeah, things are not so bad, because large SO libraries appear when we compile really, for example, large modules or large jar files with a lot of methods. If you took something much smaller, like Hello World, the resulting library will be smaller. That's good. We can take something in the middle. For example, we can look at what methods are actually executed like during Hello World startup. Okay, we can take that methods and create library from them. Or we can look at classes that are most typically or considered most commonly used during, again, startup of different applications, and create precompile methods from that classes. The resulting library, again, will be not too big. All right, so let's look at most commonly used library. I hope you use AOT. That's Java.base module compiled in a SO library. So you see that the large part of it is shareable. Most space is occupied by code, but there are also other parts. All right. If you look at library using some tools that work with libraries, what will you see? Of course, you will see some sections, and there will be definitely ones that are specific to AOT, Hotspot AOT, and you will easily find that just by looking at their names. And if you look particularly at the code, you'll find something very familiar. You'll recognize some Java methods, and of course there are some service things, because we work with AOT, we work with coupling native code with VM, and it's a code produced by some Java compiler, Graal. So you'll see some JVMCI artifacts, AOT, something, etc. And of course, for many cases, you'll see traps or de-optimization calls, etc. All right, so we'll take this huge library and try to start with it, right? So you can do it in at least two ways. You can try cold start or warm start. So if we talk about cold start, where you got nothing in your file caches, you're in a bad situation. You see here that you just waste 12 seconds for nothing. Well, you just added some configuration to your VM and you spent additional 12 seconds to wasting it, just wasted them. Well, for warm startup, the situation is better. You lose a little. It's significant number if it's relative, but in absolute numbers, it's quite small. Well, AOT must do a startup faster, right? Something is wrong. Well, we'll try to look at least at something what's wrong. For Hello World and other tiny applications, the problem is there are, of course, extra costs of loading and using library. So we do all regular Java stuff and also doing extra work. So that's reasonable. That's a trade-off of current implementation. Okay, so that's library again. And we looked at libraries that are, that the code transits to a JIT compiler, or it just doesn't, right? We may look at something in the middle. Again, we don't want to deal with huge libraries. Can we look at smaller ones? Yeah, we can profile not all the methods, but just some. What ones? Let's look at it. For example, we may filter and ignore some simple methods because their code is already good enough to exclude them from JIT compilation to make it reasonably both good for startup and for steady state. And profiling code makes library bigger, which is not desired. Okay, if you look at the Graal code for AOT, you'll see that it's all determined by some strategy that can be configured, and for example, by some standard properties that I mentioned. And if you look inside, there is no magic. We just look at what's being compiled, what's the current graph. For example, we may look at if are there any class casting loops, calls, etc., something that makes method complex, and then just it must be recompiled in that case. If it's simple, it may be not. The problem here is that if simple method is hot, it won't be inlined, and that's not very good, of course. Okay, so what can we get out of there? It's Graal, it's written in Java, and it deals with your code. And you want to configure what and how to compile. So you can easily do something really hard here. At least you may collect statistics of your code. Like you have your module or library or something, and you want to understand how it's better to use AOT with it. Well, just go and get statistics. What you're interested in, right? Here we can just plug into Graal phase and collect, for example, statistics for a number of nodes in methods. All right? Let's patch Graal. In current implementation, it's possible to patch the Graal that's used in DM. Okay. That's a good diagram. I like it. Have you ever expected that there are such large methods in Java.base module? I didn't. Okay, let's stretch it a bit. Let's use logarithmic scale. Looks more informative, and then just cut the significant part. Yeah, right? Then you'll see that the number of simple methods determined by default heuristic is actually quite low. What can we conclude here is that there's no significant impact on performance. There is definitely an impact on library size, so think about it. All right, what else can we use? Flame graphs or other profiling tools. It's native code, I mean, generated as libraries, the AOT code. So you can use any tools that you work with native libraries, and methods in that libraries are real methods, I mean, in the format of so library. And for example, you can do just simple stack sampling, just use perf or whatever. By the way, you can visit talk by Nitsan Vakart about flame graphs with more details. Whatever. We'll take our code, run it div Java 9, div AOT and without AOT, and note that there is no agent that maps native addresses to Java method names, or there was no implemented agent some time ago when I checked. So what we'll see? Wow, flame graphs. Okay, in a big scale, we may notice that then AOT is used. There is no wide and very deep stack part. It's an eliminated interpreter, so that's very good. There is some part left, and it's a task for Hotspot team, of course, to eliminate all of it or most of it. If you look into in detail, we'll notice that I'm not sure if it's clearly visible, but if it's just no AOT run and no libraries are used, the stacks will show unmapped addresses. So that will be mostly interpreter right here. It's in a startup of some application, so it will be interpreter and JIT compiled code. And if you use AOT with debug information, you'll see really, if it will be AOT without debug information, you can aggregate samples by library names. So that's the upper picture. And you basically do nothing for that. It's for free. Sometimes it's useful. You may just quickly conclude what's the amount of time spent in your particular AOT compiled part. Or you may consider that at the same time would be spent if it's not AOT compiled. Sometimes it's useful. And for other parts, the picture will be the same. You'll see some unknown missing map files. Well, that's it. And if you leave debug information with your library, you'll see all full qualified names of your methods. Right? That's good. Okay, let's return to performance. So what we've seen is that sometimes it's good, right? Sometimes it's comparable to performance of JIT compiled code, and sometimes it's not. Probably measurement of throughput is not so good idea. Okay, let's measure startup. We'll take some simple application, well, Java-C. It's single-threaded and it deals with a lot of objects and does something useful. And we'll compile small or, not so small project. Do you see the difference in time? Isn't it impressive? It's a 25% difference. Well, there is a little star there. They forgot something. It's a configuration with many threads. And if we use just one thread, the picture is not that good, right? What happened? And you see also that baseline is quite different. By the way, the middle column is Java-based AOT compiled, and application is AOT compiled with tiered support, and the right column is non-tiered case. So in a good variant, non-tiered case gives, of course, even better results, and that's actually a hint on what's going on. We save a lot on profiling just because some cool implemented feature in AOT and Graal where we don't do profiling too often. So in method, when we profile, you may decide whether or not do profiling for entire method. And inside that method, there are some points for profiling, right? For collecting counters for the M. And where you also choose for each of them how often do notify the M about counter change. But you may decide not to profile the method at all at some points. That will greatly reduce contention and strip off all other profiling logic. And that says a lot, actually. Implemented such a thing in C2 is, well, more complex and dangerous, but for AOT and Graal, it works pretty fine. Well, of course, if you talk about something probabilistic or etc., there is logic that calculates that randomness. It's a parent G, and it's again a waste of your processor time if there is only one active thread, right? So switch it off. All right, what are other parameters? So they are all here. Is that basically there are similar ones for individual counters for tier 2. And for AT, you have some more. Right. Okay, let's continue the profiling costs. We'll try to estimate this cost and compare the entire performance, at least in some case, with C2 and C1. Okay, so we'll take tiers from tiered, right? That's C1 with different amount of profiling. We'll take C2 and non-tiered and tiered AOT. And tiered AOT will be configured to stay in AOT as long as possible. Currently, it transits to tier 3 and tier 4 anyway, but we can postpone that process. So that's a approximate picture, right? But still we can relate and compare and see that, yeah, full profiling is quite costly. And relative difference between AOT with profiling and AOT without profiling is similar to what we'll see with tiered, then basic profiling is involved, right? It's C1 and tier 2. Okay, in contended case, you see that tier 3 profiling is extremely expensive, but AOT profiling default configuration is, well, again at the same level, right, as C1 and tier 2. Okay, so what's the warm-up? Maybe here it will be, well, extremely good. Yeah, expected result was that warm-up will be much better with AOT. I talked about it. But we see that the curve of warm-up, it's time of single workload paths from iteration to iteration. So it decreases, of course, because application warms up, compilations happen, etc. And we can use AOT or just run with tiered or just stick to C1, right? So C1 will definitely show a faster warm-up, but the steady state will be worse. Well, still it's not bad, right? It warms up. Currently it's slightly worse than regular tiered, but it depends on the benchmark, and I think it's to be refined. If I summarize the time for some iteration to reach that iteration, for example, it will be a warm-up scenario. Then you not limit your warm-up by time, but doing fixed workload of iterations. You'll see that again, tiered AOT is comparable to regular tiered. Well, that's not bad. That's good. And you can also modify thresholds that influence warm-up of your applications. Again, they basically are similar to thresholds for tiered, but defaults are different. To stay in AOT longer, I'll start up, of course. And again, the same picture is then Graal is used as JIT compiler. Well, I think it's also not bad. There is no gain here, but having the same picture is probably good. Okay, so we looked at different parts, and still there is some problem with AOT code. Maybe we'll try to find that out. What happens? What blocks us in some cases from good performance? But in other cases, there is no problem, right? We saw that in some spec benchmarks, the score was the same. Okay, so it's time to talk about micro benchmarks. We'll try to estimate some simple things, but we worked with a new compiler and new VM configuration, so there are a number of caveats, then we try to work with it. The scenario will be quite simple. We'll take some color and Kali, right? There is also a benchmarking harness with benchmark code, and we can precompile both color and Kali, or one of them, in a single or different SO libraries, right? So that's the setup. Here's a big table of some results. First, we'll try to estimate the cost of a call. We'll do just a call to some empty method. What will happen? You'll see the information here is nonsense, because, of course, calls inside VM should be cheaper than any other options here, like calling from SO to SO. So something is wrong. But still, we can get some useful information. We see that relatively they are the same, right? That may be false numbers, but the order of magnitude is the same. And also we can look at hotspots and see that, yeah, there is something definitely related to runtime, but the amount of that work is very small. And there's definitely something there that's related to AOT library, and an amount of that work is super small. That's good. What also do we see here? We see that there are some C1 parts. That means that we use tiered compilation, and some versions of our Kali method are in C1, and that gives us at least bimodal distribution of results, and that makes no sense of the resulting numbers. Yeah, let's fix it, right? We'll just turn off tiered compilation, and now numbers look better, but still something is wrong, right? You see that left column is not the list. Okay, let's look next. Time to look into the code. What's there? What are hot places being executed? We see that in known AOT case, we execute harness, we execute caller, callee. That's good. And in case then AUT is used, we see that, yeah, there is a SO library, but the final target is missing. What happened? What are your guesses? When a method disappears, it just wasn't lined. You saw that in the initial setup, there was a bunch of annotations about, well, don't inline, etc. But it's something that was made by JOTC in Graal. So that annotation just didn't work, right? So we can force this behavior. It can be done by two ways, but currently only one of them is really working. Anyway, so we force our benchmarked method to be not inlined, not optimized, so they may be considered, empty method can be just removed, right? We don't need a call. So what will happen? Yeah, we'll see that nice empty method in a SO library, and we finally get some meaningful result. You'll see that, yeah, there's a cost of a couple nanoseconds per call. Around 1. That's on weak machine, so not bad. What else is interesting here is that there's no difference between calls from one SO library to another or inside one SO library, at least for small libraries. For bigger ones, it seems like there's also no meaningful impact of dealing with one or multiple SO libraries. That's an interesting topic, actually. Okay. Let's consider another benchmark. We'll read a length of string field from another class. Right? We'll have two classes with data caller and class of data, and we'll access data from another class. Okay, so what we'll get here? Yeah, and the other option may be reading not something string related, but just some data like primitive integer, for example. You see that there is 1.5 difference approximately. Maybe that's a real problem. So what do we have here? It's a simple scenario, right? The amount of data is small. We do very basic thing. And we get 1.5 difference. Can it lead to 10 or 20% difference in benchmarks? Yes, it can. Let's look on some processor counters that also differ in the same way. We see that there are a lot of cache misses and branch miss predictions. Well, maybe not so many, but much more than in basic case. Then AUT is not used. All right, let's look at the code. What native code is hot? You see two methods. One is produced by C2 and the other by AUT. That's visible, and you can see that, yeah, that's a method from some library. And they differ 3 times in size. Well, I thought that Graal is effective compiler, right? Why the method is so big? Because of AUT specific. It's a problem of current implementation. Let's look at this method, right? What we will see there? a lot of specific parts where jumps may be made related to possibly uninitialized classes. So if we deal with some class and method, we must first initialize it at first invocation. But first invocation with AOT is the same as the other invocations, right? So we have checks for initialization and then branches for doing that initialization. And then we deal with some class data. Then we, of course, need to get information about that class. So we have an extra level of indirection. And also, there is some nice logic for strings. So that's the problem. Yeah, probably it's, yeah. I forgot to mention that in C2, you'll see just constants, right? Because dynamic compiler knows where is your data. What's the address of field, of some, what's the offset, what addresses of classes, are they initialized or not? They are initialized if the code is hot, right? So constants versus indirections and etc. What can we do here? Why is there such a problem, right? The AOT code is shareable. So they use exactly same code with multiple instances of virtual machine. There's, of course, read-write part of library, but code is read-only. It's not patched. Maybe it makes sense to patch it, but then we'll get additional cost of patching and lose sharing. Or maybe we actually know that constants. We actually know constant values or can build an execution in such way that all that addresses will be known. Yeah, and the third point here is that good methods are good. If you use arithmetic, arrays, etc., not dealing with objects, yeah, you'll get good results. I mean, performance results in benchmarks or, you know, of your real code. So, what's the impact of that problem? We can just gather statistics. When we look at Soul library for Java.base module, and look how often do we see such places where we access dynamic data. Well, in average, it's quite often, right? You see that per method, there are like 5 places that will add additional logic to that method in case of AOT. But the interesting part is that not so many classes are involved. So it's not 100% coverage of classes. And if you just take that classes and try to create, for example, shared archive for them, we'll see that it's not that big. So why do we talk about shared archive? Shared archive is of class data is memory mapped, and it's already structured as an internal structures of VM. So in this case, if you work with this archive during AOT compilation, you know all the offsets. And you also know that all classes from that archive are initialized, right? Because you start this that archive and you already loaded it. So no initialization code is required and no extra interaction level is required. Okay, so div.java.base. If we took that classes that are involved in such checks and create shared archive, we'll look that it's relatively small. I mean, relatively to SO size. And that means that if you generate both shared library and shared archive, the entire size will be smaller. And we can produce code that's more effective and will get better performance. Okay, but we already have some shared archive for basic classes, which is produced for default system CDS. Then you type java -x share dump. Does it contain same classes or not? Well, it's distributed like in this line. So there's some shared part and some unique parts. No big luck here, but there is some intersection. Okay, so I mentioned inlining. Does it really matter? Well, at least it matters if we talk about size of library, right? Because when we do inlining, we inline and create multiple copies of same code. What else? Yeah, and we can just compare that sizes. You see that, well, difference is noticeable. But what will be the performance impact? Well, we can just turn off inlining. I mean, inlining done by Graal when AOT compilation goes. And we'll see that in some benchmarks, well, there'll be just no difference. But of course, in some cases, the difference will be large. Again, that's tens of percents. Okay. Yeah, a couple of words on GC. There is some GC overhead for AT, but it's, well, it won't be noticeable in real applications. Maybe there's something good. Let's return to startup. Yeah, sometimes you can see good results of the startup, but sometimes not. So we can basically AOT compile java.base, tiered or non-tiered, and try some applications and see that, well, typically smaller ones with hundreds of milliseconds in execution, considered the startup time, there will be a positive influence. Sometimes not, and interesting case here would be what happens if Graal is used as JIT compiler. So, yeah, you see Graal bootstrap here. Again, most impact is done by compilation of java.base. There is actually a small difference between compilation java.base and compilation of everything, like Graal, JVMCI, etc. But it's, well, few percent and maybe neglected. Okay, and for larger applications, the influence may be more noticeable. Like we had experiments with WebLogic in a basic setup. It really depends on your hot path, because recent changes in WebLogic made difference to be close to 0. Well, not close, but at least much smaller. And here we definitely saw that there are savings of CPU resources. So in configurations like Docker or big machines, it definitely makes sense. Okay, and it also combines diff upcds, where you save both startup time, so savings from upcds and from AUT are summarized. And we can save some footprint on startup because of smaller code cache and shared code from AUT library. Okay, what's next? You heard about the problem. So what's good is that it's known and it has to be fixed, right? It probably makes sense to combine that support of AUT in other products, like cloud products. And of course, to extend support of ahead of time compilation to other platforms. So, okay, so you got AUT. It's open, it's free, non-commercial. Well, for now it's for one platform, but it's already in JDK 9, it works. Sometimes it allows you already to get better results, sometimes not. But there are known problems and they have to be fixed. You're welcome. Okay, do we have some time for questions? Yeah, questions, please? Well, no questions? Right. Well, thank you.